All right, so I would say we can start now. Thank you everybody for joining us today. So my name is Yannick Schillinger. I'm working with e-learning and capacity building at the United Nations University in Bonn, Germany. And as you might already know, we are hosting this webinar series in the GlobeDrought project. And today I'm joined by two of our colleagues from the project partner at the University of Göttingen. And they are focusing on agricultural drought and how they are impacted by, how agricultural systems are impacted by drought, how we can detect drought in these systems. And so I would like to hand over to Hamideh, who will give the first part of the presentation.
Thank you very much.
Maybe I can't hear you.
Can you hear us? Can you hear me?
Yes. Yes, no, it's better. Can you make sure to speak directly into the microphone?
Yeah. So did you hear me, or I should have?
It's kind of on and off.
Okay, I go over. Hello, everyone. Good morning, good afternoon, good evening, wherever you are in the world. I am Hamideh at the University of Göttingen, Germany, with my great colleague, Dr. Rezaei. We are very delighted to present part of our results and challenges that we face in the project called GlobeDrought.
Sorry, Hamideh, sorry, excuse me. I think there's something wrong with the connection of the microphone. Like sometimes I hear you well, and then it drops again.
Okay, process. We are trying another microphone.
Sorry, everybody. We're just trying to get another microphone. It worked before, but apparently something is not working well. So while they're changing the microphone, I can just let you know that you're free to write any questions you might have during the presentation in the chat. And later we will have a Q&A section. We will address the questions, and also you can also ask questions then. But you hear me, right? Yeah. I think the presenters are still trying to connect the other microphone.
Can you hear us, Yannick? You need to talk very closely to this one.
I'm very sorry for the problem. Yeah, you hear me? Yeah, do you hear me? Okay, good.
Yes, now it's really good.
Okay, as I mentioned, I'm here with my colleague, Dr. Ehsan, to share the results and challenges of the project GlobeDrought today. In particular, we focus on agriculture and research. Introduce yourself.
Hello, everybody. My name is Ehsan Rezaei from University of Göttingen. I am an agronomist with a keen interest on crop modeling, and today, my colleague Hamideh said we will present our latest results, GlobeDrought project. So I will hand over to Hamideh. She will start with the introduction, and then we will present two different case studies regarding to this project. And please.
Okay. For those of us private from media, how but here we have a collection of some cover pages of mainstream media and the oh, there is a. Is it better now? Okay. Yeah, here we collected some cover pages of media that reflect on drought and its importance and extent. As you may know that there are several definitions of drought. To be on the same page, let's go over the definition that we use in this project. What we call drought here is an exceptional continuous period of deficiency in soil moisture that results in extensive damage to crop growth and production. In this project, for the first time maybe in the global scale, we have a distinctive definition of aridity and drought. What we mean drought here is a temporary recurrent climatic feature of abnormally dry weather long enough to cause a significant hydrological imbalance. However, aridity refers to long-term moisture deficiency and dryness when the water demand is greater than water supply. I want to highlight here that for us, drought and aridity are not the same. As you know, there is an extensive literature on the number and frequency of drought events at regional and global scale. Here we refer to one of the recent studies that plots the number and also frequency and total economic damage of drought events at the global scale for the period of 1960. What I want you to notice here is the increasing number of drought and the frequency over time. Okay, if you by any chance attended to other webinars in the project, you know that we are a large team that we focus on different aspects of droughts to have the final product that is drought risk assessment. We divided different aspects of drought into three main pillars of hazard, exposure, and vulnerability. And today, we are from hazard team, and we focus only on this aspect. I want to mention that in our group, we mainly work with models and remote data to monitor and map hazard aspects. To make sure that we have clear vision of how different they are, here we map risk and hazard and exposure and vulnerability for the period of 1985 to 2016 for the whole globe. As you can see, in the top part, we have risk map. In the bottom, part B shows the combined pillars of hazard and exposure, and the right side, part C, you can see vulnerability. I think I don't need to highlight how different they are and how the impacts are different in different parts. If you are interested in this study, you can read our papers in the journal that we recently published.
So, hello again. I will continue with the case study 1. That in this case study, we look to the global drought pattern using a modeling approach. And we would like to see how the droughts are different for different crops at the global scale separately. And we also would like to explore the performance of the model integration of drought signals in different regions. The crop model that we use in this study is Global Crop Water Model, which is WM. And this model is relatively simple, have relatively simple structure with low level of parameterization required. The only yield reduction factor in this model is drought stress. We run the model with using 2 different climate data sets. An older data set come from CRU in the period 1985 to 2016. ERA 5, most recent climate data, 1981 to 2008. And the global extent that we use and the resolution of the data that we use is 5 minute times 5 minute grid cells. And the crop model used the Penman-Montes FAO 56 method to calculate the potential evapotranspiration. The main outputs of the crop model is actual and potential evapotranspiration, and the ratio assumed as a drought indicator. But to find out the real drought, we use the crop drought indicator, which is the relative deviation of the ratio between actual and potential evapotranspiration specific year compared to the long term. Water use and yield are also other outputs of this model that we didn't consider in this case. So let's have a look on the drought pattern at global scale over the years. You can see in this animation how different is the drought simulated with this model over the time. You can see how the temporal and spatial pattern of the drought change over the time, from the extreme drought to the extreme wet conditions over the period. So, but which years are the most extreme years in terms of droughts as output of this model? Here in this plot, you can see the ranking of the years from the high ranks, from the year 1 to year 38, and we highlighted 3 years as the most dry years across the study time. The driest year in the period is year 2012, the global scale. This year is the year that North America experienced historic drought because of La Nino episodes. The second very extreme year is year 1987, which is one of the most dry years in South Asia, and mainly in India, that 85 million people will severely affect. And the third year is year 2018, 2 years ago, which Northern Europe experienced a super extreme drought, which is record-breaking with any terms. If you see the frequency of drought events before and after year 1995, you can see number of drought events increased a lot in the recent years. And it seems the number of drought frequency increased a lot when we are going out during the time. But let's compare the wet and dry years for different regions across the globe. North America, Western and Eastern Europe, and then Southern Africa and Australia. The top panel shows the most wet years in the study period 1996. And if you compare this with the dry years, most dry years in the study period 1985 and 2012, you can see how different, how the range model detects to find out the drought signal. So, but what does this drought signal means to the real production, to the real observations? We compare our drought indicator with production net rate and domestic supply quantity for the 2 years before the drought event, 2 years after, for cereal crops, oil crops, and pulses. In this case, we pinpoint North America year 2002. And if you see these panels that we got from FAO statistics, you can see the year 2003, the production of these 3 main important food crops reduced a lot compared to the 5 years. At the same time, net trades also goes negative. The region needs to import, but there's no big change in domestic supply quantity. The total loss of this drought in North America is $3.3 billion, and the yields and the production of cereals reduced by 13% compared to 5 years. We also check other regions like Australia. See, at the same year 2002, there is a very large reduction, production and net trade and domestic supply quantity. And the most interesting point is the net trade, the drought effect on net trade appears 1 year later than severe drought happens. The total loss for this year was around 2 billion, and this drought also came with extensive wildfire and 45% reduction for cereal production in Australia detected for this year. But what about South Africa, Southern Africa? Because the 2 cases that we showed before are from developed systems, but Southern Africa is developing system. And you can see year 1992 is one of the super extreme droughts happened in this region. Our model could nicely detect this, because when we compare this with FAO statistics, we can see the difference of this year compared to the other years in terms of production and trade. Almost 50% of reduction in production of major food crops detected for this year compared to the 5 years. More than 1 million people were affected.
Most of us that we work with agricultural systems, one of our major questions when we are dealing with drought, if different crops and
please remember to speak a bit louder to the microphone.
Okay. We want to know whether there are differences in long-term trends of drought stress for different crops in different regions. What you see here, animation of crops here, wheat, maize, barley, potato, rice, and rapeseed. You can see the differences, the changes in the drought in potato over time for the period 1986 to 2006. As you can see, there are big differences between crops in different parts of the world. To highlight these differences, in the front plot, you can see what we plotted here is 3 most extreme years of drought for different crops. Yeah? In the x-axis, you see 25 crops that we study in this model over time, like from 1960. What you see here, we selected 3 different colors: red for the most extreme, yellow for second most extreme, and blue for third most extreme. What I want you to notice here is we have different extreme years for different. For instance, for wheat, the most extreme year is 2006, while for maize, it's 2012, and etc. In this part, we plotted median and a standard deviation of our drought indicator. As Ehsan mentioned earlier, as a result of our model, we have actual eating potential. The ratio is what we call drought indicator. So we plotted median and a standard deviation of 25 crops for 22 regions. Based on US geoscale, the whole globe was divided to 22 segments. And in order to see the effect of drought and aridity on these regions, we plotted these two graphs that you see. What I want you to notice here is, for instance, if you go to Western Asia, you see that most of the squares in the column are red. But for the same in the left part. In the right part, if you check for the same region, you see that most squares are blue. And the whole point is that Western Africa, which is Middle East, is more suffering from aridity than drought. In another attempt, we want to show you how drought and aridity affect different countries and different crops. Yeah? Here we mapped of our drought indicators against a standard deviation, or two axes. And you can see that countries are positioned in different part of this. On the top part, basically, there are countries that they are humid. In the bottom, our countries are located in arid and semi-arid climate. Also, if you look at the west part, are the countries that they are less prone to drought, while in the right side they are more prone to drought. But what I want to show you here to see the difference of affection of drought for different. In this slide you see wheat, and in the next slide I show you maize. If you find the position of Germany here, you can see that, of course, it's a humid country and not many drought areas. It's not prone to drought. However, it's a different story. Germany, of course, is humid, but it's more prone. And it's the same story for most other. The other analysis we want to show you the trend of aridity. So you
Sorry, Hamideh, we can hear you.
Yeah, for 25 crops in these 22 regions. Y-axis shows these 25 crops, and 22 subregions are in the x-axis. If you look at Southeast Asia, Southern Africa, and Western Europe for the crop wheat, you can see that there is an increasing trend of aridity. One of the other questions that we wanted to answer in this project is checking the strength of the correlation between drought indicator and reported drought. What you can see here is what we plotted the correlation coefficient between yield and our drought indicator. Again, in the plot, y-axis we have 25 crops, and in x-axis we have 22 regions. What I want to highlight here is to see that for different crops, the correlation is totally different. For instance, for maize or sorghum, you can see that there is a high correlation between yield and our drought indicator for Central America, North America, and Western Africa. But for some crops like cotton, grapes, oil palm, and sugar beet, there is a very low correlation for instance, for Eastern Europe, for Northern Europe, and South America. Our the message that we want to show you for the first case study that was entitled Modeling of Drought in Global Scale, we want to highlight that drought risk is chronic and region specific, and we need to know that because if we want to set a drought monitoring,
so we can barely hear you.
yeah, if we need to set up a drought monitoring system, we need to distinguish between these differences. Also, we found a correlation between simulated drought indicator and reported yield for drought prone.
So again, let's jump into the second study. The second study, we would like to see how our model results related to the remote sensing observations. The main objectives of this second case study is investigating the relationship between simulated model-based range of the drought, remotely sense-based drought indicators at regional scale, because we didn't have the capacity to find out what's going on at the global scale. Particularly that we need to have remote sensing data at global scale, which is super hard to analyze. And we also would like to assess a relationship between yield and the remotely sensing drought indicator anomalies for South Africa as one of our test regions as a super drought prone. What we did here, we run the model as we explained at the global scale, and then we extracted data with the help of our colleagues in ZFL, remote sensing of University of Göttingen, University of Bonn. Then they help us to extract a set of remote sensing indicators at the regional scale, the period 2001 to 2018, USA, South Africa, and Zimbabwe. And the main products came from the satellite imageries of MODIS. So, what we find out, we first plotted the anomaly between our drought indicator and anomaly of the remote sensing indicator. We have standardized precipitation index, normalized difference vegetation index, the normalized difference infrared index, and albedo. When we run this for USA, we find out SPI3 and land surface temperature, LST, have very high correlation, and this NDII6 have very high correlation with our simulated drought indicator. But the question is, are these indices are consistent over the regions? And we need to test this methodology for other regions, other environments. Then we had a look on Zimbabwe. We had more or less same story in Zimbabwe. The land surface temperature showed very high correlation with our drought. Same albedo showed the lowest correlation with our drought indicator. We did the same study and the same analysis for Southern Africa, and we find out, again, this land surface temperature showed the consistent relation to simulated drought indicators across the environment. It means land surface temperature could be generalized as one of the most correlated indicator with drought, even at the global scale. But what about merging this indicator? How the merging this indicator? Have a look on the multiple correlations. We did this analysis for South Africa. First, combine the NDII6 with LST and find out this weighted correlation 0.65. With adding the number of indices, the correlation coefficient. Which means even when we got the low correlation for albedo, it doesn't mean this information is useless. When we aggregate these indices together, we can get a better estimation of the drought over the region. The combination of the RS indices, the relationship between remote sensing anomaly and simulated drought. But what about yield? How this related to yield? We had a look, we extend our study for South Africa to see how the anomaly of yield correlated to different remote sensing indicators, our drought indicator. If you have a look on the green line, you can see again this NDI6 and land surface temperature showed the highest correlation, even one negative and one positive correlation with the yield anomaly. This is even higher than the correlation that we got from simulated drought indicator. Find out there was a strong relationship between remote sensing indicator and yield anomaly. So what are the take-home messages out of this second case? First, land surface temperature is the most consistent detecting drought across different regions, including USA, Zimbabwe, and South Africa. The anomaly of RS indicators highly correlated to crop model results. At regional scale, selected RS indicators have strong correlation with observed yield anomaly. So we talk a lot about the strengths and efficiencies of our modeling and remote sensing. But what about the limitations? One of the biggest uncertainty that we have in this type of studies is the land use change. The problem is we don't know how the land use changed over the time during the study. We have one crop yield mask, which is static, but the farmers change the crop that they cultivate over the time. The second limitation is the dynamics of the change among irrigated and rain-fed areas. Constant ratio between irrigated and rain-fed areas. But we know on the ground it changes. But globally, there is no information about the dynamic of change, ratio of irrigated and rain-fed. The third limiting point is change time of sowing and harvest over the time. Model, but generally it changed by the change in crop characteristics, change in cultivars, the last point of uncertainty or limitation in this. So thank you for your attention, and now we are open for questions about this.
All right. Thank you both for an interesting presentation, and apologies to everybody again for the sound that sometimes kept disappearing. But I hope you were able to understand everything anyway. And if you have any questions, just put them in the chat now. There's also a button on the top to raise your hand if you want to speak your microphone. So from what I see, we have one question by Rezaei about the slide that showed like on the global scale, the risk, hazard, and vulnerability. About how confident we can be that the vulnerability can be expressed at country level, that exposure and hazard are on that much finer resolution. Like, are we not missing any regional differences in this approach?
Okay, let's read the question then. Question about global risk. Okay, maybe I can respond to this question. Yes, we had different resolution for vulnerability and risk and hazard. The problem is the vulnerability information always came at the country scale, but our model usually run the grid-based level. And when we want to aggregate this information, we usually need to aggregate this very high resolution model outputs to the country scale. That's the main reason that we have different resolution for different maps. Okay, the next question.
Thank you.
Okay, the next question regarding the crop choice. Yes, we can find out which regions are suitable for which crops. But please be considered. We only look for drought strain. For many of the crops, drought is not the main yield limiting factor. For example, in Western Africa, drought is not a problem. The main problem is nutrition. We can climatically say this region is suitable for a specific crop. But when we want to go to the farm level to understand is the crop really work at the farm level, we also need to have information regarding to the management, other cropping aspects.
Thank you. And I can see that Nada is asking about a link. So yes, we will share a recording of this webinar. And I think there's also going to be a short lecture video, like a narrative presentation.
Okay.
There is a question about the link that you mentioned. We forgot to mention that there will be a lecture by next week. We upload it about this topic. So if you are interested in this topic, please check that Yannick will inform you.
I can see some other people are still typing, so good.
Okay. The question I can see about SPI3 from John. Yes, SPI3 was a bit disappointing, but not for US. For US, it works very well, but for South Africa, it didn't work well. And this is the point is some of these indices are region specific, some of the indices are general, and this land surface temperature looks very consistent over the environment. When we want to generalize and specific indices at the global scale, it would be better to use indices that showed good performance over the environment. Yes, regarding the drought and irrigated system, we have cropland mask for irrigated and rainfed for the year for around year 2000. We take out grid cells that assign to the irrigated conditions using this cropland mask, and that's the limitation of the model. We don't know how it changes. The rainfed area and irrigated area may change over the time, then this could change our results as well. But at global scale, there is no information of dynamics of irrigated and rainfed areas.
Yes, John. If you are working on a regional scale, maybe you don't look for irrigation. Maybe you can get a crop cover map for your region, and then you overcome this problem.
Okay, I can see a question about India. Yeah, India is a specific case because of amount of irrigation that we have in India. I think for India, it's not to rely the output of this type of demand because the irrigated lands, extent of irrigated land is very high. And there is another complication in India. Irrigation for many regions means we don't have drought stress. In India, even if you irrigate it, the irrigated water may not enough to overcome the drought stress. And that's why we cannot super rely on output of global models, particularly when we assume no change in irrigated. Yes, smart agricultural. We got another question about the smart agriculture. Yeah, that's a procedure, but in smart agriculture, I think we need to have a look on the many different aspects, like management, socio-economical aspects, are the labors available on time, aspects that we need to consider on smart agriculture. And we can do this at the regional scale. Global scale, we cannot have one solution for a global scale. But if we go to the specific scale and specific regions, then we may go in the direction of smart agriculture.
I can see there are several people still typing. If anybody would like to speak on the microphone, you can also just click on the button to raise your hand. Maybe it's quicker. Otherwise, yeah, I can see Rezaei has shared his LinkedIn profile. We can get in touch later. And Vinay,
Okay. I think typing would not be very easy. I think this is a question from our colleague in India. Yeah. Now, can you hear us? Just say yes, then I can repeat the answer. Yeah, but please feel free to send message to us in LinkedIn or email if you want to continue the discussion. We are pretty open for this. Nada. Thank you for. I think is this a question or a statement?
it's more like a comment or observation.
Okay. I see. Yes, that's right. Usually drought stress came with heat stress at the same time. And, as an agronomist, I can say just go a bit about the crop physiology. When the drought happened, the crop closed stomata to reduce the water loss due to the transpiration. Then crop getting warmer because the energy exchange would not happen with transpiration. This maybe kind of additive impact on yield reduction when we have drought condition and high temperature at the same time. Okay, I put my LinkedIn address here if anybody interested to continue discussions. Because of time limitation, they're very welcome.
Right. So we still have 10 minutes in case there are any further questions. Otherwise, has posted the link for his LinkedIn, so if you want to get into contact. Also, Hamideh.
For here, discussion, or if you have any question about this project, I'm more than
All right. It seems like there are no further questions. So thanks everybody for joining. And as we've said, there's going to be the link to the recording of this webinar. And also there's going to be a separate video lecture that is coming out maybe next week. Yeah, it was nice to have you all here, and you can also write more questions or comments in the discussion forum on the learning platform. If you go to the learning block of this topic, you also signed up for the webinar. And otherwise, we will send out another mail invitation for the next webinar, which is hopefully going to be maybe at the end of this month or beginning of the next month. Yeah, hope to see you there.
Okay. Thanks a lot for listening us, and
thank you very much for your time and your contribution. We are hoping to hear from you about this presentation and the whole project. And also, please check the link that Yannick sent to all of you about our image. Thank you.